Hello,
Good afternoon, sir.
good afternoon, everybody.
Good afternoon, sir.
So everybody joined. Hello.
No, sir.
No, sir.
Okay. Let them join. We will wait for 2-3 more minutes.
Will be absent for today class.
Hello. Okay. So we will start now. Is it visible? Hello.
Yes, sir.
Number कौन सा?
Okay. So today we will do experiment number 9 to verify different mode shapes in whirling of shaft. Is it visible?
Yes, sir.
Yes, sir.
Okay. So we will start now. So this is the setup that we have for experiment of whirling of shaft. You can see that here one shaft is attached to two ends, and there is a motor which will rotate the shaft, and we will try to find the critical speed in this shaft. So to find this critical speed and to do this experiment, we will divide this experiment into 3 parts. At first we will try to understand what is the critical speed, and after that we will try to get the what will be the equation for this system that you can see here, that this shaft is a continuous system. So what is the equation for continuous system? And in third section of this video we will try to we will try to match the theoretical frequency with the practical one that we will going to perform over here. So coming to the first part, we will first try to understand the critical speed. So in any shaft, as you know, no shaft is perfect. Okay, so there is some type of we can say that eccentricity in that shaft. So due to that eccentricity, what happens? Some due to that eccentricity, some deflection at the time of using that shaft is occurred. So suppose if we have any kind of misalignment in the center of gravity, so that will generate an eccentricity. You know that mr square is the formula for deflection of that, like what to say, the centrifugal force. Mr square is the formula for the centrifugal, and mr omega square, and that will there will be also a restoring force due to the shaft is our shaft is the so look here, we are going to perform whirling of shaft. So critical speed is the speed at which the shaft tends to vibrate violently in the transverse direction. So we will do this experiment, and I will show it to you by drawing the diagrams. Suppose this is our shaft, and this shaft is fixed at the two ends. When we rotate this shaft, what happens? Due to this eccentricity, you can see here, I think picture is not clear. It's not clear now. So due to eccentricity, what happens? The shaft gets deflected, and when we rotate this at high speed, due to the centrifugal force, you can see here, this shaft gets more deflected, which ultimately generates some bow shaped. You can see here, this is a bow shaped, and this ultimately changes from one bow to two bow. We can also say it as a loop. So this will ultimately change. For the first time, if the loop is there is only one loop, so this will look like this. Okay, when there will be generating two loops, then in that case something this kind of setup will be there. Okay, so we also call this phenomenon as mode. This is mode. Number of mode here is equal to 1. Here number of mode is equal to 2. So what happens whenever this gets deflected? You know that there is one centrifugal component, that is m r omega square, and when there will be, because the shaft is stiff, so due to the stiffness, this shaft will also try to restore the whatever the deflection it has got. This will try to restore that. So the restoring force will be stiffness into whatever the deflection has occurred so far. Like suppose initially when the shaft is at rest, so shaft will be straight, and when the deflection is happening, the shaft will go something like this, like some deflection will be there, and there will be two components. One will be the centrifugal and the restoring component. This component will, in a case of spring, what happens? There is some kind of restoring force, which is K into X. Then the first K into, similar happens to this shaft also. Due to the stiffness of that shaft, the shaft will try to restore its position, and centrifugal force due to the speed, you can say that mr omega square, this will try to deflect the shaft and restoring force will restore. It's a main phenomenon that is occurring there. So now we will try to understand the concept behind this. So basically, I have told you earlier that a shaft is a continuous system. So in any continuous system, we have some governing equation. Like, let me tell you the first that what is a continuous system and what is a discrete system. For a mass block system,
Sir,
you
your
can see.
screen is not visible and audio is not all coming clearly.
So is it visible now?
So from previous
Hello?
case also everything which you explained, it was not clearly visible and audio was also it was breaking.
Is it visible now? Hello? Hello?
Yes, sir.
Thank you. So for this
Previous page
continuous
can you
system, the equation.
the previous page can you
Okay,
explain once which you have written?
okay. So what I was explaining is अच्छा फिर से मैं वो ड्रा कर देता हूँ. Okay, so what I was explaining, is it audible?
Yes, sir.
Hello. So what I was explaining was, suppose we have a shaft fixed and we are trying to rotate this shaft. In that case, what happens that if any shaft has some kind of eccentricity, then in that case, what will happen? Shaft will tend to deflect. If we are rotating this will ultimately what happens? This will be deflected. And while deflecting, why this is deflecting? Because that eccentricity part, like suppose some eccentricity is there, suppose y is the initially the center of mass is deflected by y, and due to this, when we will rotate, this will generate an extra eccentricity. Suppose y plus e. E is the amount which is getting deflected after we are trying to rotate this. So in this case, what will happen? That an extra restoring force will be generated. Suppose this is the position when this shaft is rotating. One component will be the restoring force, and one component will be the centrifugal force. Centrifugal force will be whatever is the position of this point at this moment. M. Suppose I'm calling it at R, mr omega square, and restoring force will be S into Y. What suppose Y is this deflection at this point of time. Okay, so these two components will work on this, and we know that the shaft is a constant. In that case, the governing equation for a continuous system goes like this. This is partial differential equation, and you might have known the method for solving a partial differential equation. If not, you will know to how to solve this in these classes of sir. Okay, so this is the governing differential equation for the continuous system, and here our continuous system is shaft. And the equation, after solving this equation, applying appropriate method, you will generate a solution. You will get a solution which will give us the formula of critical speed. Okay, suppose I'm saying omega I is equal to 2I minus 1 pi by 2L into root over E upon rho. So A is the Young's modulus, rho is the density, I is the number of mode which I can be from 1 to up to n. So this is the formula of critical speed, and by the help of this formula, with the help of this formula, we will get the critical speed, critical speed, and we will try to compare the theoretical with the practical one. So suppose I'm writing, change करें please. So using this equation, this critical speed formula, omega I is equal to 2I minus 1 pi by 2L into root over E upon rho. So for I equal to 1, suppose there is one mode, then the critical speed will be, at the place of I we are keeping 1. So 2 minus 1 pi upon 2 into length is 1 meter. Okay, and here we are assuming that the shaft is of mild steel, so the Young's modulus of the mild steel is 210 GPa, and the density of the mild steel is 7840. After, and I am putting 1 here since this is a for mode equal to 1. So for first mode, the critical speed will be something around, if we calculate, let me calculate this, pi upon 2 root over 210 into 10 to the power 9 upon 780. So you can see here that the value is 8129. So this is, and now we will convert this. Okay, later we will convert this into our RPM. Okay, this is a critical speed. This is critical speed, and we will convert it into RPM. Okay, so now for second mode, we will get the same equation as 4 minus 1 pi upon 2 into root over 210 into 10 to the power 9 upon 7840. And when we will calculate this, let me calculate pi this is 2 sorry 2438.93. So these are the critical speed at first mode equal to 1, and this is at mode equal to 2. And unfortunately in our system we will be able to show you up to 2 modes only, so there will be no third mode in this system. There may be, but this is a little complicated to show you third mode, so we will show it to you for the first mode and second mode only. So let me draw an observation table first. So Now we will draw the observation table. In our observation table, first we will write mode, and then we will write theoretical frequency, or then we will convert it into RPM, that is theoretical one, and we will compare it to the actual RPM. Okay, actual RPM and in the setup. Okay, this is setup. So for the first mode, and second mode, the theoretical frequency that we have got is 8129.64, and for second mode we have got 24388.93. And when we will convert this into RPM, let me convert it, then I will tell you. Okay, so for the first mode, the RPM is 1293 RPM, and for second it is 3881 RPM. And now we are going to the third part of this video, that is the we are going to show you using this our setup available here. So now we will start this experiment, and we will try to verify the theoretical RPM with the practical RPM. So now we have apparatus like here you're seeing the setup, and here one motor driver is there. Okay, and now here we have a motor that will basically rotate this shaft, and to measure the RPM we have a tachometer, you can see here, and we also have a digital tachometer, you can see here, that is basically works on the principle of infrared. Okay, sorry, you can see the laser here. Mhm. You can see the with the help of laser this device operates. We have this. Okay, so we will this is the setup, and we will try to now measure the actual RPM of this setup. So now we are starting. Please start. You can now see the first mode, that is you might be seeing the one loop which is like this. This is the first mode, and now this mode will shift to the mode two modes. Okay, so if we'll speed the increase the speed, then this will shift to number of mode equal to 2. Okay, two loops will be generated, and we are going to apply this tachometer at this point. And applying this, we will get the value of our RPM. You can see here. Okay, so this will generate our RPM. Okay, like setup is 750. So for the first mode, when the mode will shift,
लूप एक ही है अभी
come, mode shift हो रहा है, कम करिए. Now you will be able to see there are two modes. You might be able to see. Okay. Now at this point we have only one mode, so we will try to measure RPM at this point. Okay.
लगेगा लगेगा
Sir, once use the digital one also.
Okay. Okay. We will use that one also. Let's stick to one mode. Are you hello? Are you guys able to see two modes here? Hello. Hello.
Yes, sir.
Yes, sir, we got the idea.
yes sir
Okay. Okay. So we will measure the RPM for the first mode as well as second. What happened? So this is 1400 RPM. You can see the black one. It's saying 1400 RPM. Okay. Now we will increase the speed so that we will get two modes. You have seen the mode shape like this. Okay. This you have already seen. Now we will see like this. What happened? Sorry, we got our setup disconnected. The connection.
हाँ इसको आगे पीछे से करना
We are going to run this setup again. So we have successfully measured the RPM of this vibration at mode 1 and mode 2 mode, 1 mode and 2 modes. Okay. So you can see here that theoretical RPM was something around 1300, and we also have got around 1400. That you have already seen that it was something below 1400. So approximately 1400. We have approximately done this, and this also you can see we measured this with the help of our mechanical that tachometer, and this was done theoretical. Yes, but I'm talking about the tachometer. We have done this with the help of our laser tachometer, because at such a high speed it is like tends to like nearly impossible to adjust that tachometer with this vibrating system. So that was hard for us to be in contact, to keep in contact the tachometer with the shaft. So we tried this with digital tachometer and this with mechanical tachometer. So you have seen that we have verified these two. So if you guys have any questions, then you can ask your questions. Okay. Hello, anybody?
Yes, sir. Since the starting only, the rod was in first mode. Like it was making one loop since the
Yeah.
starting mode.
No, no,
Then how
no.
did we calculate
Yeah.
1400 as exact?
When the mode starts shifting to the second, okay. Hello. We are not
Yes,
calculating.
sir.
We are calculating the critical speeds. Okay, this is critical, and the definition of the critical speed is when the shaft tends to vibrate violently in the transverse direction. When the that mode became violent, we are measuring that speed. Okay. It is obvious that from initial it will be in the first mode only. Did I answer your question? Hello.
Again, please. I was unable to
What
listen.
again? Okay.
So,
Okay. Okay.
a bit
So from starting only, this shaft was in its first mode. But when the shaft, the definition of critical speed, you know already that when the shaft starts vibrate violently in the transverse direction, that is the definition of critical speed. So we measure the critical speed, not the like general speed. From the range of speed, the shaft will be in first mode. Like there will be generated one loop for a large number of speeds, but we are going to measure here, we have already measured the critical speed when the shaft starts moving violently in the transverse direction. Okay.
Changing from one mode. Shifted.
Yeah, when it shifted to from first mode to number of modes from this shape to this shape. Got it? Hello.
So when it was just about to move from first mode to second mode, then it was the critical speed of first mode.
Yeah. When it again try to say again another shape, then this vibrates violently. Okay.
Okay, sir.
Any other one? Any other questions? Okay, so we will end this session now. Hope you see you to see in next lab, and you can note this data. Thank you.
Sir, can you
Thank
send
you,
all
sir.
the photos which you have written?